Hi everyone, I am Shovik Kundu. I am a PhD student at the University of Southern California. Today I will be talking on the topic Spike-Thrift towards energy efficient deep spiking neural networks via attention guided compression. With our increasing dependence on AI driven applications on various platforms like GPU, CPU, and ASICs, demand for energy efficient solutions have increased rapidly. This is mainly because the extreme computation demand of these applications has a heavy carbon footprint in our society. To that end, brain-inspired spiking neural networks have gained significant traction in recent years due to their low power promise. The spike-based SNNs are functionally more similar to our brain as opposed to the conventional ANNs. Also, these SNNs promise extreme low power solution through suitable event-driven hardware. Two major sources of their reduced energy are: 1. Extremely sparse activation maps. 2. They require only accumulation instead of multiply accumulation, which is around 32x more energy saving in 45 nanometer technology. Now we discuss the need of model compression. One major reason is AI-enabled IoT devices are mostly resource and energy limited. Also, most deep neural network models are over-parameterized and thus efficient compression hardly affects the accuracy. Finally, the biological neurons of human brain are sparsely connected as well. However, model compression in SNNs has some major challenges. In particular, aggressive pruning is difficult to achieve without compromise in accuracy. Iterative SNN pruning becomes extremely time, memory, and energy consuming due to their backpropagation through time approach. Thirdly, non-iterative sparse learning techniques suffer from non-convergence issue as well due to the absence of batch normalization layer. Thus, efficient model compression technique in SNN is largely missing. If we delve deep into the non-convergence issue of the SNN models, we find gradient explosion is a major reason. We now describe the broad level idea and our SNN compression framework that successfully solves the previously mentioned issues. In particular, we propose the idea of guidance through an unpruned meta model to prune the constraint ANN that is conversion friendly. We term the mechanism as attention-graded compression. In the two-step compression, we first perform compression of the model under consideration by guidance of the attention maps of the meta model. Here, we follow the sparse backpropagation to ensure the cardinality of the non-zero weights are satisfied. We then convert the ANN to SNN via standard firing threshold evaluation technique. Finally, we perform a sparse SNN training to achieve better accuracy at reduced time steps. In specific, the ANN loss function has two major components: attention transfer loss and cross entropy loss. We also update the mask of the pruning dynamically, similar to sparse learning strategy. We start the SNN training by taking the mask available from the end of the ANN training and keep the mask value static throughout the SNN training. For details of our proposed training technique, please refer to the paper. We now look at the results of our proposed scheme. It is clear from the table that we can now achieve ultra-high compression and of the SNN models of up to 33x with negligible accuracy drop. Compared to the existing SNN compression and training schemes, we perform better in terms of accuracy and compression. To evaluate the computation energy benefit of the SNN models, we use a more comprehensive formulation of the floating point operation. From the figure here, we see the SNNs generally have more flops compared to the isoparameter ANNs, which is due to its inference over multiple time steps. However, the compute energy is much lower compared to ANNs. In conclusion, we can say that our proposed AGC can provide aggressive compression with negligible accuracy drop. Our non-iterative hybrid sparse learning strategy reduces the time and memory demand of SNN compression. Finally, we resolve the non-convergence issue with sparse learning of SNN via attention-guided compression. Thank you and hope to see you in the Q&A session.